Alright students, welcome. Let's take a quick look at some of the beginning pieces of A4, Rigid Body Mechanics. We'll also look at some of the guiding questions. Go ahead and read them through. The understandings for this topic are here, and we also have some guidance for it. These are all here for your reference. The linking questions when we look at other topics and how does this relate to other topics. And finally, our formula booklet. So let's jump into this a little bit and talk about linear and angular displacement and velocity. So in this case, what we're going to do is we're going to look at the rotational dynamics of it, which means that we have our displacement S is equal to R times our theta, where theta is in radians. And if you've looked at circular motion already, you'll know that theta has an analog, or in other words, from kinematics we have velocity is equal to the change in distance over time. And from our uniform circular motion, we can say that the angular velocity is equal to the number of radians per unit time. And that's exactly what this S is telling us, that this S is actually, excuse me, radians, our theta in radians times the radius of the circle. That's going to give us the linear distance of it. So this could be a linear and angular displacement conversion here. With these two statements, looking at speed, distance, and time, and angular speed, distance, and time, or angular speed, angular distance, and time, then what we can say is that our speed is equal to the change in distance over the change in time, which is our definition of linear velocity. Then our delta r theta, which is the radius times the radians, that's going to be our distance divided by time. Then what we can do is we can say our r is going to be constant during this rigid body rotation, which means we can pull it out of the equation. It's not going to have any deltas in front of it. And then we can say that the definition of angular velocity, because you'll notice this delta theta over delta t is our omega over here. This little w is omega. So our r omega is the definition of angular velocity. So we can now have a conversion between linear velocity and angular velocity. And in this case, the omega is in radians per second. The angular velocity in this case is also going to imply a direction. It's given by the right-hand rule, or one of the right-hand rules that we have. And what we can say is just to grab the axis of rotation with the right hand, and if you curl in the direction of the rotation, which in this case if we have a spindle here turning, we can curl our fingers in the direction of that rotation. You'll notice your thumb points down. This is going to be the direction of this angular velocity. That's the direction of omega here. So let's try one here. Find the angular velocity of the Earth. Well, for the solution, we want to say that our number of radians that we move through is going to be 2 pi radians. That's all the way around the circle. Our time is going to be 24 hours, and that's going to be converted to SI units as 86,400 seconds. And then from the definition of angular velocity, we have our change in radians and our change in time. We can see that our angular velocity then is going to be equal to that distance divided by that time. In this case, when we talk about our distance divided by time, we can start plugging in our numbers here. Our delta theta, which is going to be our distance around the circle in radians, and our time is going to be our time in seconds. We can get a value and see that this is radians per second. The small angular speed, or in other words, why can't we feel the Earth spinning? Well, interesting thing is we're spinning with it, right? Our direction, if we're looking at the angular velocity, if we wrap our fingers in the direction of the turn or of the rotation, we can see that our angular velocity points upwards. Or I guess north, we can call it. The other thing we can start talking about is the relationship of acceleration. So if we have our acceleration is our change in velocity over time, we can say the angular acceleration, which is our alpha here, is going to be our angular velocity or change in angular velocity over change in time, and where our alpha is in radians per second squared. Sounds familiar. We also know that our speed is equal to the radius times the angular velocity. So what we can write then is that our definition of linear acceleration, we can substitute in for linear acceleration with our relationship of the radius times angular velocity. Take our r out because the r is always going to be constant. And then we can say that this is going to be equal to our alpha over here. This is our definition of angular acceleration, so we can use this as a conversion as well. We can also remember our kinematics equations. What we're going to do now is we're going to take these kinematics equations and look at the angular versions of them. We're going to use these conversions where the linear distance is equal to the radius times the radians. Our velocity is equal to the radius times the angular velocity, and our acceleration is equal to the radius times the angular acceleration. Those are the definitions we just looked at. Now what we're going to do is we're going to replace these values up here with angular values. So you'll notice they're exactly the same. But for all the velocities, we've added in our omega, and we have omega initial and omega final. We also have radians final, and we have our time squared over here. This all should hopefully be familiar to you. These are all just the angular versions of those same kinematics equations. These are all represented in your data book too, by the way. So let's take these and try out a practice problem then. Find the angular acceleration of a bench grinder's cutting wheel if it reaches 2,500 RPMs in 3.5 seconds. Pause the video, see if you can try it out first. Come back in a moment. Hopefully you've paused for a moment. Now let's take a look at what we're doing to solve this now. The first thing is we have our initial angular velocity of 0. Our final angular velocity is going to be 2,500 revolutions per minute. And what we can also do is we can change this per minute into seconds. So what we're going to want to do is to say that our 2 pi radians on top and our revolutions on the bottom is going to get rid of the revolutions here. And our 1 minute on top and our minute on the bottom are also going to go away. So we're going to be left with radians per second, which is exactly what we want. Pretty cool. The other thing we can do is solve for our angular acceleration. Now that we have our radians per second, we want to look for the angular acceleration. That's our angular velocity divided by time. This is our final minus initial of the speed, our angular speed, and we're dividing it by the time that it takes in 3.5 seconds to give us 75 radians per second squared. Let's do another one. Find the angle through which the cutting wheel rotates during its acceleration. So the angle through which the cutting wheel rotates, well, this is going to be in radians over here, and we can actually change this to degrees. So we can use the first or the last formula here, this one or this one. What we can do with the first one here is we can plug in our initial speed, our time, our 1/2 of the acceleration that we just found, and our time to find that final angle of 460 radians. So this is exactly like Suvat. And for the last part here, it says find the tangential acceleration of the edge of the 5.0 centimeter radius cutting wheel during and after acceleration. So the tangential acceleration is going to be that angular acceleration. In fact, the tangent is going to be linear. So the tangent to the side of the circle is going to be the linear version of that acceleration. So they're asking for the linear version here. So remember, our linear acceleration is going to be equal to the angular acceleration times the radius. So during the acceleration, we have an angular acceleration of 75. We can plug in our 0.05 in our SI units from our 5 centimeters times our 75 that we found for our acceleration to give us our speed. So after the acceleration equals 0, what we can say then is that our acceleration, again, our a sub t, is our radius times the angular acceleration. And our angular acceleration in this case is 0. So we end up with, during the acceleration, it's 3.8 meters per second squared. And after the acceleration, it's 0 meters per second squared. Another part here when we're talking about finding the net acceleration of the edge of the wheel, well, we know the radius of it. The time that it takes in this case is 0.08 seconds. So when we plug in, what we're going to look for is the net acceleration of the edge of the wheel. So that's going to be the total radius of it. So the net acceleration, so that's going to be our a naught and our at, or the beginning acceleration or during. Then we're going to net those two together. So for the solution then, what we can do is once again multiply the radius times the acceleration. We know that during the acceleration is 3.8. And so at time t0, or time 0.08 seconds, we can say that with our Suvat formula here, final is equal to initial. This is our v equals u plus at. Plug in our numbers to get 6.2 radians per second. So then once we have our radians per second, then our radians per second is the angular velocity. Then we can use our angular velocity times the radius squared to give us 1.9 meters per second. Once we have our 1.9 meters per second, this is our angular acceleration. So then our a net squared is going to be equal to the c acceleration, which is going to be our beginning acceleration. This is going to be our ending acceleration, the one from here, our after the acceleration. We're going to take that one, square it, plus the during, and square them to get our net as 4.2 meters per second squared. And that's going to be that linear acceleration in both cases. One of the other pieces we want to talk about are rotational mechanics graphs. So one of the things you'll notice over here is that we have the angular velocity and we have time. And the graph is showing us how the second equation of rotational motion is derived from the graph of angular velocity versus time. And the angular displacement is equal to the area below the line of the graph. And if we add those two areas together, it's going to give us this equation. So if you see graphs like this, don't be frightened, but see if you can actually derive them and use your knowledge of Suvat and your angular versions of them. Let's try an example problem. Pause the video here and come back in a moment. All right, hopefully you've paused. In this case, what we're looking at is the idea that the angular velocity stays the same during the section where it's flat. It goes up in this section, and then of course then it stays the same again. So what does that graph look like? This is our time, here's our velocity. Let's get into moment of inertia now. The moment of inertia can be exemplified by using a bowling ball. So consider a bowling ball here sitting on a tabletop. In this case, it's got a kinetic energy of 0. And if something is rolling, or this bowling ball is rolling, we might say that it's rolling maybe on a frictionless surface like on ice. We can say that its kinetic energy is not 0, but it doesn't have any displacement right now. So neither ball is rolling, so they don't have any translational kinetic energy. Excuse me. The second ball only has rotational kinetic energy. So we're going to make the difference, or make the differentiation between these two. So we have a center of mass of the spinning bowling ball is not moving. It's literally just staying there. And each particle of the ball, not in the center, has some velocity to it, so it has some kinetic energy. So in translation, every mass particle has the same velocity. In the case of rotation, it's not so. So each mass has a velocity that's proportional to its radius. This is very similar to what we saw in circular motion, where the ones on the outside are moving much faster linearly. So in fact, we can see that from circular motion, if you remember this, each particle has a rotation, is rotating the extended mass with the kinetic energy of half mv squared. And our half mv squared, if you remember with angular velocity, has that radius in it. So the farther you are away, the larger this value is going to be. So what we're going to do is we're going to combine these two together as our m and our r squared and our omega squared staying on the outside. And in this case, if we're given that the angular velocity is the same, which means the rotational velocity is the same for all particles in a rigid extended body, we can say that the total kinetic energy then is going to be given by our half I. In this case, the I is your rotational inertia, or the moment of inertia, times the angular velocity squared, and the I is actually going to be the sum of the mass times the radius squared. So if you look at this, is actually nested inside of this I right here, and that's how we get from this equation to this equation. Turns out that the moment of inertia has the same function as our translational inertia m has in translational motion. So we can sort of look at this as an analog between I and m. Later we can see that the translational kinematic and dynamic equations are directly translated from their rotational counterparts. So in this case, let's practice with a dumbbell here. Find the moment of inertia of the dumbbell about its center. Each end has a mass of 15 kilograms. Assume the 30 centimeter handle is massless. So between these two, what we're going to do is we're going to use that formula and figure out finding the moment of inertia, or solving for I in this case. Each mass is 0.15 meters from the center of rotation. So the first thing we're doing is cutting this in half. And so we're finding that center of rotation. This one's animation's a little lopsided, but you get the idea. If you remember, our I is the sum of all the masses times our radius squared. So the sum of one of the masses on one side times the radius squared, and when we say sum like this, we're going to add the other one together as well to get our 0.675 kilogram meters per second. Moment of inertia. Let's do another one. If the mass from the previous example rotates once in 2 seconds, what is the rotational kinetic energy? So now that we have the moment of inertia, can we find the kinetic energy? Well, if we say that our I is the one we just calculated, let's jump in and see if we can find EK. So our angular velocity then, remember, is the radians per second, and that's going to be 2 pi if we go all the way around the circle per every 2 seconds. And that's what we got from our problem up here. That's going to give us 3.14 radians per second. That's going to be our angular velocity. So now we've got our I, we've got our angular velocity. Let's plug in. And when we plug in, we end up with our 0.675 times 3.14 squared to give us a final kinetic energy, 3.3 joules. Can you verify this? Let's try another practice question. If we take the mass from the previous example, it not only rotates once every 2 seconds, but it translates, which means it moves sideways like this, at 0.25 meters per second to the left. What is the total kinetic energy? So now we're going to take the kinetic energy of the rotation and of the translation, this is the linear velocity, and put them together. So we just calculated the rotational kinetic energy as 3.3, so let's keep that value and just look at how to calculate the translational kinetic energy. Well, our translational kinetic energy is half mv squared, and if we have our half, here's our m plus m times v squared, and in this case we say 0.25 meters per second to the left. Well, we're going to get 0.94 joules. We can add the 2 joule amounts together to get the total kinetic energy. So in this case, we end up with something like 4.2 joules. Pretty cool, right? Now we've got translational and rotational kinetic energy. Let's do another one. Find the moment of inertia of a dumbbell about one of its ends. Each end has a mass of 15 kilograms. Assume the 30 centimeter handle is massless. So this is the same problem, but now what we're doing is we are having it rotate around one end rather than around its center of mass. So how are we going to do this one? Well, one mass is 0 meters from the center of rotation, and the other mass is 0.3 meters from the center of rotation. So when we plug in, we can say our 15 times 0 squared plus 15 times our 0.3 squared gives us our kilogram meters per second. And so that's going to be our moment of inertia. So the idea that the moment of inertia depends only on the mass distribution, but also the axis of rotation. So be careful with that. When we look at some moment of inertia samples here, what we want to look at is how do things rotate about their center and what are the formulae that go along with them in order to calculate them. So one of the things we can see here is we've got our moment of inertia is our mass times our radius squared, which is what we were just working with. And this is the formula that we're going to use for a hoop. If the axis is going right through it like this, so it has a radius r, and here's our axis going right through the middle here. If we have this hoop, but it's rotating about a diameter, then we're going to use a different equation, and that equation can be seen down here at the bottom as I equals 1/2 of mr squared. So what'll happen is you'll have reference to these values, and you'll get to know some of these so that you can remember them on the test. So the second one here, when we're talking about a disc and a cylinder, this is our disc or a cylinder. You'll notice that it has a radius here. If the axis goes through it this way, this is going to be our 1/2 mr squared, very similar to this one down here. If we look for a disc or a cylinder where it has an axis like this, then we have an r and we have a length, which is this spot right over here on the side. We're going to have our I equal to 1/4 of mr squared plus 1/12 of the ml squared. For spheres, it's going to be a little bit different. We're going to be looking at the moment of inertia of a solid sphere with an axis going through the top like this as 2/5 mr squared. For a spherical, let's do this one next, an annular cylinder or a ring, what we have is we have a cylinder like this, but we have a hole in the middle of it, and we have an axis here. It's going to give us another formula. That one's going to be 1/2 m times the r1, or the first radius squared, plus the second radius squared. And so that's going to account for the difference in mass, or how much is the mass. For the last one here, the spherical shell, or in other words, this is a sphere that has a shell of a specific thickness. The thickness in this case is not going to be specified, but we have something like a shell like this. We can look at the moment of inertia of it as 2/3 mr squared. Pretty cool stuff, right? So let's practice with our bowling ball again, with our rotational or moment of inertia. Find the moment of inertia of a 7.27 kilogram bowling ball about its center of mass. A regulation bowling ball has a diameter of 22 centimeters. If it revolves twice each second, what is its rotational kinetic energy? Pause the video and come back in a moment. See if you can solve it yourself, and then come back. Alright, hopefully you've paused it. We can use the rotational inertia formula for a solid sphere. So if we look back, we can see the solid sphere formula here. Let's use that one. And that's our 2/5 mr squared. So we end up with 2/5 times the m times our r squared to get our 0.035 kilogram meters per second. And we're really looking for the kinetic energy. So once we find our moment of inertia, we can plug in for our kinetic energy. The kinetic energy then is half of our moment of inertia times our angular velocity. Remember, angular velocity is distance over time. So if it revolves twice each second, that means that it's revolving at around the sphere, or once all the way around, every half second. So I didn't want to skip a step here. And that gives us about 2.8 joules. When we talk about the rotational moment of inertia of a thin rod, well, we can also look at the moment of inertia with an axis like this, sort of going through one end of it like that. A thin rod about one end, and this is going to be parallel to that thin rod. We can say that the moment of inertia is 1/3 of ml squared, and the L in this case is going to be the length of the rod. The thin rod about the center is going to be our 1/12 ml squared, and that's the very center. And notice that 12 is similar to what we saw in spheres as well, or in the case of our round objects. For something like this, like a slab, where we have either a rhombus or a rectangle, we can say that the slab about the center, if it's perpendicular to that, and this is flat or orthogonal at 90 degrees, we can say again that that's 1/12 m, and we're going to talk about the length and the width here. So let's do an example of that. Find the moment of inertia of a 125 gram meter stick about its end. So we're going to use the end formula here. See if you can do this one and then come back for the answer. If we use the rotational inertia formula for a thin rod about its end, we can plug that in here, as our moment of inertia is equal to 1/3 ml squared. This is 1/3 times our mass times the length. We know the length of a meter stick is a meter. We can end up with 0.042 kilogram meters squared. So the moment of inertia about the end of a ruler is more than that about its center. Why is it more than that about its center? And the idea then is because the mass is making up the ruler, on average, is farther from the pivot point in the former case. So in this case, it's farther from the pivot point if we connect it right over here on this side. The next topic we'll look at is torque. So we'll look further into that next time. For now, try out some practice problems and see how you go.